So these forces that are listed in this table are ones that have to have specific labels, very specific subscripts. When there's other outside forces acting, like I push or I pull or something like that, you can label that as force applied. You can label that as force push, force 1, force 2. That sort of a force that's an outside force that's not one of these can be labeled in a variety of ways. Okay, and I'm not really specific about that. I usually label applied forces with an F and then sub APP for applied, but that's just how I do it. These forces, however, have to have a specific subscript. So we looked at friction a little bit in our lab simulation, but friction is always labeled F sub little f, and it always goes in the direction opposite of the motion, right? So it always should be counteracting the motion or trying to slow it down. So friction always has to oppose the motion. The normal force, we talked about that in our last class at the end. Does this box right now have a normal force acting on it? Yeah, because it's resting on a surface, right? The surface is exerting a force in the upward direction against the box. Now does the box have a normal force acting on it? No. Okay, if I'm suspending this box in the air, it does not have a normal force because it's not resting on a surface. Okay, so if I was holding, let's say I'm holding this box up like this, can you tell me what types of forces I'd have acting on this box right now? Gravity, force due to gravity, and also what? Yeah, a pull or a tension force or whatever, however I'm holding this. Okay, these are something called free body diagrams, and these are essential for our force problems. Free body diagrams are the way we draw a motion diagram for our force systems. Okay, these are very, very, very important. Okay, so free body diagrams allow us to make a pictorial model of what we're trying to represent. We're trying to look at all of the forces at one time as compared to the system. Okay? So when we're dealing with a free body diagram, a lot of times your book tells you to circle the system or indicate the system with a dot. Okay, and that's usually how I indicate the system, is just with a dot, rather than trying to draw a book or draw a whatever they're trying to tell me is being acted on, whatever the system is. Usually we can just indicate it with a dot. Okay, you are more than welcome to circle it as well if you want, but you indicate that system with a dot, okay, or a box or whatever you want. It's not very, it's not a big deal if you want to draw the picture, but it just kind of wastes some time. Okay. What we want to do is we're going to identify every place the system touches the external world. So we want to find out every single force that's acting on this system. Okay? And this particular free body diagram has some different labels here, some different subscripts, some a little bit more layman term type subscripts. So if we were going to label these forces with things that we know what they're called, what would we label this upward force, the force of the table acting on the book? What would we call that? The normal force. We would call that the normal force. So that would be labeled F sub N, always a capital N. Okay, always a capital N for the normal force. What about this force right here, which is pulling us downward, Earth's mass on the book? What would we call that? F sub G. Good. Right? That's our gravitational force, or our force due to gravity. The force of our hand on the book could be called force push, force applied, force hand, whatever you want to call it. This is a little bit more specific than I usually get. I don't like to have more than one word in my subscript, but that's up to you. Okay? Just because they're going to be putting into net force equations and having all of those subscripts that are like sentences long are unnecessary. Okay? All right, so we want to identify every single force acting on our object. We draw our forces as vectors in the direction of the force. Okay, in the direction of the force, they're drawn as vectors, which means they need to be drawn proportional to one another. Okay, if we know that the net force of our system is 0, that means we need to make sure that the vertical forces cancel each other out and the horizontal forces cancel each other out. That needs to be, that means they need to be drawn to the equal magnitude. Okay, they should be the same length if we know they cancel out. Okay, and tell me, when are the two instances when our net force is equal to 0? There's two instances in which our net force is 0. I know it's been a little bit. Take a look back in your notes. When should net force equal 0? If it's at rest, good. And when else? If it's moving at constant velocity, good. So net force is equal to 0 if we're at rest or if we're moving at constant velocity. Okay, because moving at constant velocity means we have no acceleration, and we know that net force is equal to mass times acceleration. Okay, that's Newton's second law, mass times acceleration. Okay, so when we draw a free body diagram, we draw them as vectors, and we draw them in direction of the force. Once your forces are drawn, you can identify the object as a dot. That's what we talked about at the beginning. You can indicate the system as a dot. Okay. Let me make one more thing clear. When you're drawing a free body diagram, forces or the vectors should always go away from the system. Away from the system. They should never point at the dot. Okay, so here I've got an applied force to the right. My force should never be drawn like that into the system. It always goes away. Okay, so the tail of your force vector should always start at the system and go in the direction it should. Okay, never draw a vector into the system like that. That's like a big no-no. Okay, away from the system. We want to make sure that we label each and every force, whether it's F sub n, F sub g, F applied, whatever. Every force has to be labeled, and vectors should be drawn to scale. They should be pointing away from this subject. So that's what we just talked about, or away from this system. Okay, so we don't ever see the gravitational force look like this. Okay, that's not how it works. It needs to go away from the system. So tail of the arrow or tail of your vector needs to start at the system. Okay, let's try some free body diagrams now. You're going to become really, really good at drawing free body diagrams because you need one for every single force problem that you do. Okay? So we're going to start out really simple, and then the practice we do today will get a little bit more complex, but we're still pretty much dealing with only horizontal or only vertical or things like that. Okay? We're not dealing with forces at angles yet. Okay? So let's see, I want you to draw the free body diagram of a box accelerating in the rightward direction, and we want to include frictional forces. Okay, so you can start with a box, you can start with a dot, it doesn't matter. Okay, either way we're going to have some system, and it's accelerating in the rightward direction. Okay, it doesn't tell us how, whether it's being pushed or pulled or whatever, but we know that it's accelerating in the rightward direction. So that means we know we've got to have a force that's going to the right. Okay? And we can label that whatever we want. Okay? It doesn't tell us anything. I'm just going to call that force applied. Okay? Or APP. Because there must be some sort of force that's making it go in the rightward direction, that's making it accelerate. Whether it's a push or a pull, we weren't told, but there's got to be some non-zero force that's acting, right? So if we're going to include frictional forces, frictional force should then go which direction? To the left. To the left. Okay, and should it be longer or shorter than my applied force? Shorter. Should be shorter. And this is why. If we are accelerating in the rightward direction, that means our applied force in the rightward direction must be greater than our frictional force because it's overcoming friction and it's able to gain speed. It's able to accelerate. Okay? If we were moving at constant velocity, what would be true of these two force vectors? If we were moving at constant velocity, what would be true of those two force vectors? There could still be friction if we're moving at constant velocity. They would be what? I'm sorry, I can't hear what you're saying. Okay, is this particular box escaping gravity at all? No. So we still have to have a gravitational force, and it has to be resting on some surface in order for it to slide, right? It's not going to slide in the air. So what force must be acting in the upward direction? Normal force. Okay, tell me what we know about these two forces, the normal force and the gravitational force. They should be equal to each other. So F sub g should equal F sub n. And the reason for that is because it's not accelerating in the upward direction. Okay, vertically it's at rest. Okay, vertically it's not moving up or down, which means the normal force and the gravitational force must equal each other. Okay, does that make sense? So in our picture, our applied force is greater than our frictional force. And our gravitational force is equal to our normal force. Okay? So just because an object is at rest doesn't mean all four of these forces have to equal each other. That means the up and the down have to equal each other, and the right and the left have to equal each other if an object's at rest or it's at constant velocity. Does that make sense? Okay. I need you to ask questions if you have any. Let's try another one. A car is coasting in the leftward direction and slowing down. Coasting in the leftward direction and slowing down. Our system, I'm not going to take the time to draw a car. It's coasting in the leftward direction. When you coast in your car, are you applying any sort of force? Okay, it's slowing down. So if it's coasting in the leftward direction, what must be the only force that's acting on it? Friction. And friction would be going which direction? To the right. Very good. Okay, so I'm slowing down in the leftward direction. I'm not applying any force because I'm coasting, but friction has got to be going to the right to slow me down. Okay? And then what about our vertical forces? Do we have any vertical? What do we have? F sub g and F sub n. Oops. So what do we know about these two forces? They're equal to each other because this car is not bouncing. It's not accelerating in the upward direction, so we know F sub g is equal to F sub n. And we know that our frictional force is the only force that's acting in the horizontal direction. Okay? Any questions? Okay. We're going to talk about